Okay, this is number 20, and it's another Green's theorem problem. Here I'll read it from the directions. It says that C is the boundary of the annular region R. So this is your annular region. What they mean by annular region is that it's an annulus, which is this thing right here. But we're only dealing with a portion of this. So it's the annular region in the first quadrant. That's why I have it drawn that way. Between the circles of radius 1 and the circle of radius 2. So there's our region. Notice also that the region is kind of a circular region, so it's going to be better for us to use polar coordinates rather than rectangular coordinates. So we'll keep that in mind when we go to translate this integral. We're going to do a double integral. Originally what they want us to do is this integral, but by Green's theorem we can translate it to this, and this will be much easier to do. The contour that they're talking about, this C here, is going around this region, and you can see it. It's comprised of 4 different segments. So if I were to do this integral, I'd have to do a C1, a C2, C3, C4, and that's going to be a lot of work. So I'd like to avoid that by employing Green's theorem. And that's part of the directions of the problem anyway. So let's get started with it. I need to get these terms here. So again, in this setting here, this is our F1 and this is our F2. So del F2 del x is equal to, I'm taking the derivative of this with respect to x, I get 3y. And then del F1 del y, I have to take the derivative of this with respect to y, I get 2y. So the difference between them is 3y minus 2y, which will be y. So this term in the integrand is just going to be y. Okay, so let's set that up. I have a y here. And then the dA, that's where I decide whether I'm going to do rectangular or polar. In this case, I'm going to use polar. So this dA is going to be r dr d theta. That's what just this dA represents. So I've got everything I need here. What I need to put in now are the bounds. Since I've decided to use r and theta as my variables, I'm going to do r going from 1 to 2. And then theta is only going from 0 up to pi over 2. So there's the integral that I have to compute. I have one more step before I can start integrating, and I need to convert this y to be in terms of r and theta. So we use the identity y equals r cosine r sine theta. So I'm going to take this and I'm going to put it in for y. Don't forget that we have this extra r here. So 0 to pi over 2, 1 to 2, and then I have r squared sine theta dr d theta. Okay, now I'm ready to integrate. Integrating the r, I get r cubed over 3 sine theta, and that's going to be evaluated from 1 to 2. Once I complete that evaluation, then I'm going to integrate with respect to theta from 0 to pi over 2. Okay, when I plug in the 2 here, I get 8/3. When I plug in the 1, I get 1/3. So 8/3 minus 1/3 will be 7/3. And I'm going to do that integral. Okay, so I have to integrate sine theta. That gives me negative 7/3 cosine theta, evaluated from 0 to pi over 2. When I plug in pi over 2, I get 0. Cosine of pi over 2 is 0, minus negative 7/3 cosine of 0, which is 1. So the final answer is 7/3.